So without further ado, David, who's been lurking in Cambridge throughout the pandemic, I understand. David, would you like to talk to us about nanoparticles?
Yeah, sure. Thanks, Mike. Can you all see my screen? Yeah. Does it work? Can you see my screen right now? Yeah. So yeah, it's a pleasure to be here tonight to speak about some aspect of my research. So I'm currently investigating a kind of sustainable way to produce functional micromaterials directly from commercial nanoparticles. So as you may know, we currently have to deal with a lot of challenges in the society. Among them, I will focus a bit more on access to clean water, diagnosis and treatment of diseases, which is quite relevant with the current COVID situation. So a lot of work has been made in the domain of material chemistry in order to try to design new material which could help us for environmental and biological applications. Among them, composite materials have attracted a lot of interest because, as you probably know, composite materials are a combination of different materials in order to obtain a system with multiple properties. So a system, for example, combining both magnetic properties, adsorption, fluorescence, catalysis, depending a bit of what you want to do with them. So it's something which is quite known, but the problem is most of the methods you will find in literature are either time-consuming. They are sometimes quite hazardous because you will need to use toxic chemicals to prepare your system. You will need high temperatures in order to obtain the particles you want to kind of burn out some chemicals from your structure. And also, it's quite expensive. You need specific lab equipment for this process, which make it more difficult to implement, for example, in developing countries, if you are looking to it. So the idea behind was, what if we could just produce microcomposite by just selecting specific nanoparticles, so commercial nanoparticles that you can buy directly, and combining them together to obtain a system with the properties you want. So it was what we have in mind behind our project. So for this, we use a quite simple method. So preparing what we call an emulsion, so dispersion of water inside oil. And inside this water droplet, aqueous droplet, you will have your nanoparticles. So in normal conditions, those particles are negatively charged, so they tend to repulse each other. But what happens when you add the salt, you will just screen the charges of your particle and just agglomerate everything together. And the fact that you do it inside an aqueous droplet, you will obtain a spherical compound, so spherical beads. And basically, this method offers a lot of advantages. First, it's fast. We need less than an hour to prepare our entire system. It's easy because, as you can see, I just need a mixer and a centrifuge. I don't need fancy equipment for that. It's safe because mostly everything, I spent more or less the last 2 years just playing with sunflower oil from Sainsbury on water, on a couple of nanoparticles, of course, but mostly using a lot of sunflower oil. And you don't use everything is done at room temperature. So you don't have the problem for the operator to have to burn out your system at 400 degrees or so on. But I think one of the main advantages of this approach is the tunability. We observed that first, we could easily kind of tune the size of your final microcomposites, because the size of it is directly linked to the size of your water droplet. So by adding more energy to your system, you can decrease the size of your water droplet. So basically decreasing the size of your template and producing smaller particles when you agglomerate everything. We also observed that it was possible to easily change the morphology of a system. As you can see between image A and image C, we have a clear change of the roughness of the particle. And this was obtained with a quite lucky, let's say, an unexpected way, just by using some surfactants, so compounds which like oil. And we observe that those compounds tend to stay around when you agglomerate your nanoparticles, and they are later keeping some oil around. And when you washed away your system, you kind of remove the oil, creating some cavities in your system. And this was done without having to use a conventional method, which is using organic templates, so using some chemicals which are going to stay inside and you will have to burn out at really high temperatures, like 400 or 500 degrees. So it was quite a nice result. And finally, what we observed, and probably the most important results, was the fact that, as I said at the beginning, we could easily incorporate different kinds of compounds inside the structure. Basically, if you can disperse your nanoparticle inside your aqueous phase, you will be able to link them together when you produce your microbits. And this is quite interesting for the application where we can consider. So I will show you three kind of projects I worked on in terms of application. So this one was the one for which I received the CSAR PhD award. So it was the idea of trying to design a system for water treatment. As you may know, we have to deal with a huge problem of synthetic dyes in water due to their extensive use in the textile industry. So different methods exist in literature to kind of deal with, to tackle this problem. You can use method using chemicals, so trying to precipitate your compounds and waiting for the sedimentation and removing the sediments. You can try to use physical approach, in which you will have membrane on your compounds will adsorb on your membrane. Or, for example, biological approaches, using bacteria to kind of digest your compounds. But the problem of most of the methods is they are expensive, complex, and what do you do with all the pollutants you generate? For example, the sediment you have at the bottom of your tank. So it creates a real problem of sustainability. So one method which is used by a lot of more considered now, is to design system with titania, which is known as a photocatalyst. So titania has the ability to absorb UV light in order to create some oxidizers to destroy synthetic dyes. So the idea was to combine in our system titania, which can collect energy to destroy the pollutants, and iron oxide, in order to have a system which could absorb the light, destroy the pollutant, and be easily recovered after treatment using a magnet, so that you can reuse your system again and again. So the key findings, we observed that it was possible to do it. The only limit we have at the moment, on which we'll have to be investigated in further details, is the ability to catch the light. Because at the moment, we can only catch UV light, which limit a bit the application we can have. So the further experiments will have to incorporate, for example, additional elements, which kind of will act as intermediate to catch visible light and transfer the energy to titania to continue the process, which titania can't do at the moment. So it was one of the projects we have in mind on that. The second one we just started is in a totally different aspect. It's more based on what we call bioseparation. As you may or maybe not know, DNA biochemists tend to try to purify different molecules from their system, such as DNA, RNA, or different proteins of interest. The common way to do it is to use commercial kits, which are generally composed of magnetic silica beads, so compounds on which DNA can adsorb and desorb according to the pH, to the salt concentration, so that they can easily recover they can absorb the DNA, recover it with a magnet, and desorb it in another solution to kind of purify it. So this is well known. The problem is most of the commercial kits are quite expensive. And also due to the high demand, you can have to struggle with some shortage of supply, which create a real problem. So the objective of this project, developed with Dr. Jenny Malloy from the Chemical Engineering Department, was to try to see if we could produce directly our magnetic silica beads in the lab without having to rely on commercial kits, so that we can offer a low-cost biological separation technique for developing countries, for example. So the preliminary results we got are quite promising because, as you can see in the image on the left, we can obtain magnetic silica beads. So we have a system with in red the iron oxide, so the magnetic material, and in whitish the silica. So we have the system with the two elements we want. On the first test we carried out showed that it was possible to recover DNA with these compounds, which is really promising for the future. We now need to investigate to compare the results obtained with those particles with some commercial kits in order to prove that we can compete with what is commercially available. And the last stage on this project will be probably to try to investigate the absorption of different proteins to see if we can have a kind of platform to do more than just DNA. And the last project, which is really, to be honest, just like a baby project for the moment, because I just started it 3 weeks ago, is a project in partnership with Dr. Aaron Elborn in the University of Melbourne in Australia. The objective of this project is to see, can we produce a system with antibacterial properties? Because recent research have proven that it was possible to use magnetic compounds in order to kind of remove bacteria film on surfaces, which can be interesting, which is important to avoid the propagation of diseases. So in our case, we wanted to see if we could use our magnetic system doped with copper oxide and zinc oxide, which are known to have antibacterial properties, to obtain a system with basically antibacterial and also magnetic properties. So for the moment, the results you see here, you are basically the first one to see them. Even my supervisor haven't seen them yet because they are just from 3 days ago. It showed that we have a system, as you can see here, with different compounds inside, and we managed to characterize the compounds inside, the different chemicals inside, and we observe that we have a system with both zinc, copper, iron, confirming that we managed to incorporate those 3 elements together. So the next stage is going to be to screen different kind of bacteria and fungi and see if we have a match and if we can use this system to destroy bacteria. So to kind of summarize what I was presenting, so we developed a sustainable approach to produce composite materials directly from agglomeration of nanoparticle in aqueous droplet. So this method offers a lot of advantages, and among them, the tunability is quite interesting, enabling us to change diameter, morphology, as well as composition of the system, opening which open us on different possibilities, different kind of applications, from bioseparation, antibacterial application, and also water treatment applications. So now the next stage that I would like to continue to work on, that I would like to continue in a fellowship starting next year, will be basically to investigate at different size, so trying to move to nano composites instead of micro composites in order to be able to target more biological applications. So to try to design new systems, for example, for medical imaging or targeting drug delivery. But for that, it's necessary to work with systems which are maybe 10 times smaller than what I just showed you. So if you are interested to know more, you can take a look to the 2 papers we published this year on this. And I would like to thank the University of Cambridge and the BPI for the funding and the facilities. And of course, the CSAR for both the opportunity to present my work to you tonight, and also for the award they gave me a couple of months ago. So if you have any question, I would be happy to answer to you. And if you want to know more, you can contact us or follow us on different research media. Thank you.
David, thanks very much. That was great. We hear a lot about nano, this, that, and the other, and putting some flesh on the bones of what you can do with nanoparticles is rather fascinating. Now, we usually just take 1 or 2 questions at this stage. I don't know whether anybody has got a question that they would like to put.
I have a question.
John.
This is
Go
John Cook.
ahead, please.
Towards the end, you mentioned the microporosity, David. Well, it was a very interesting talk, by the way.
Thank you.
Can you tailor the microporosity to get to extremely high surface areas, specific surface areas in these particles?
The thing is that for the moment, for what I show there, we are limited to the surface area we can have due to the larger size of the particles. I mean, of the final composites, because with composite of 1 micrometer of here, 4 to 5 micrometers, you can't have a really large surface area generally. We can increase a little bit with this approach, but I reckon the best method for us would be to try to investigate different shapes of nanoparticles, not using just spherical one, but maybe using some needles, some rods, in order to create a system you see with more kind of urchin-like system, so that you can tailor even more the porosity. It's what I'm working on my fellowship application, to be honest, just to try to show the variability of that. I mean, this project is still quite new. We started to have really interesting results, mostly before the pandemic. So I think we will have way more in the couple of months now that we can finally go back to the lab and do a bit more work. But yeah.
Thanks, David. I don't see any other questions, so I'll abuse my chairman's privilege and ask my own, which is, how scalable is this approach? Can you, the level you've shown us is essentially the level of the bench, but can you do it in high volumes?
Yeah, the thing is that normally it's scalable. We still need to figure out exactly the perfect parameters to do it, because at the moment, yeah, it's a good point. I'm more working on batches in which I produce 500 milligrams, 1 gram max. Because one of the challenge of it, and you will see with most of the method to produce, for example, nanoparticles, it's if you start to increase too much the concentration, you have a high instability. So everything I try to produce, for example, a couple of grams at the same time in a small volume. And the problem is everything starts to just agglomerate together, because you start to link one aqueous droplet with another one, and at the end you obtain a massive blob. So you need to be sure to kind of keep enough free space between the system. So you have to work with more diluted concentration at the moment. But yeah, it's something which could be worked on. But for that, we will have to do more investigation on way to stabilize the different droplets together to be sure that they don't come together. Maybe increasing viscosity or adding some additional surfactant or stabilizers. So yeah, but I mean, for that, it's going to be probably a full year or 2 years of work, or maybe a full PhD for just the scaling up. For the moment, it was more proof of principle with application where we need a couple of grams.
But I think that's already fascinating that you can create essentially new materials with very specific properties, which is at nano scale, which is quite fascinating.
I mean, which is interesting. It's also the fact that if you speak with most of the people working with nanoparticles, they are more afraid of that colloidal destabilization, or the fact that you agglomerate nanoparticles together. It's what you try to avoid. So you try always to not have too much salt to try to avoid this phenomena, because it's just gelling inside your tubes. And in that case, we decided to do it inside the aqueous droplets in order to kind of have a geometrical constraint to try to. We don't control exactly everything which is happening there, but we know that it's in each droplet, so that you kind of control the instability or destabilization, which is kind of the other way around compared to what other people usually do.
That's great. Fascinating. We'll look forward to keeping in touch with your future progress.